Hello everyone, I hope you are doing well wherever you are. In this lesson and in the coming lessons, we are going to focus on rectifiers. We are going to look at the two types of rectifiers, a half-wave rectifier and a full-wave rectifier. Rectifiers are found in almost all power supplies. All your electrical appliances in the kitchen, sitting room, your computer room, they have rectifiers in them. For example, the power source of the desktop computer has a rectifier, as well as a TV, it has a rectifier. Anything that functions on DC voltage has a rectifier. So what is a rectifier? A rectifier is just a device. It is a device that converts AC voltages to DC voltages. That's why we need this rectifier, because most electrical appliances, they use DC instead of AC. Example, all electronic devices, most of them, they use DC. So we need something to convert the AC voltage we have in our outlets to DC. So that's where a rectifier comes in. Moving on, below I have drawn a circuit of a half-wave rectifier. Here's a circuit diagram of a half-wave rectifier. As you can see in front of you, the rectifier, this circuit schematic, it consists of a diode. Here's our diode. And we know that diodes only conduct electricity whenever a voltage is applied in a certain way across its terminals. It can only conduct if the voltage is applied correctly. So in front of you we have a diode. This is a half-wave rectifier, and we have our power source. The power source generates an AC voltage or an alternating voltage. Our goal is to convert this AC voltage into a constant, into a unidirectional, meaning one-way voltage. As you can see, here's our input AC voltage, and I have drawn the waveform, and as you can see, it's sinusoidal. It alternates between the positive side and the negative side, meaning the voltage changes direction. Here it's positive, negative, becomes positive, negative, but what do we get at the end after rectification? This is our rectifier circuit. After rectification, we have what? We have a voltage only in the positive direction. And look, the negative part, the negative voltage parts have been eliminated in the output side. The negative cycles of the sinusoidal voltage are not present at the output. They have completely been eliminated. And how? We know in the previous lessons we looked at how a diode works. We know that a diode can only conduct electricity whenever it is forward biased, meaning we have our battery here, our power source. Let me try to draw a battery and a diode. Give me a sec, guys. I'm still not used to using this drawing tablet. I'm still learning, So please guys, be patient with me. There we go. We know that if we have a diode just like this, connected like that, and this is our power source, we know that this diode will act as an open, as a closed switch, meaning it will conduct. Why? Because the power source, the battery is forward biasing the diode, and if the opposite is done, meaning this part is connected to that part and that part is connected to that part, then the diode will act like an open switch. That's what is happening here. It will not conduct. So whenever the AC voltage goes positive, the diode becomes forward biased and it allows that voltage to pass through, and the voltage is now seen across the resistor as our output voltage. The output voltage takes the same waveform, the same shape as the sinusoidal, with the exception that the negative part of the voltage has been removed. During the negative half cycle of the sinusoidal, the diode becomes reverse biased, and we know that a diode which is reverse biased does not conduct. That's why you do not see this negative part appearing there, because this is the part where the diode is no longer conducting, where current or voltage is not allowed to pass through the resistor. So no voltage appears across the resistor. It's zero. But once the waveform goes positive again, the diode becomes forward biased and voltage is allowed to pass through. And that's why you see this, that, and that. I hope you have understood, guys. So what this AC voltage is doing, the polarity is continuously changing. In the positive half cycle, the polarity is like this, positive, negative. But in the negative half cycle, the polarity is like this, such that the diode now becomes reverse biased. So that's what is happening. So the AC source alternates between these polarities, so such that the diode becomes forward biased in the positive half cycle and reverse biased in the negative half cycle. Moving on. So let's look at the analysis of a half-wave rectifier. It's called by now you should have figured out why it's called a half-wave rectifier, because as you can see for yourself, only it's a half-wave. As you can see, the output, and we only see half waves at the output, nothing else. So you should know by now why it's called a half wave rectifier. Now continuing the analysis, the output voltage is equals to the peak input voltage of the sinus of the AC source minus the diode drop or the potential drop across the diode. That's the so this is the amount of this is the output peak voltage at the output. So it's the peak input voltage minus the diode drop, and the frequency, the input frequency of the AC source is equals to the output frequency is equals to the input AC, the input frequency, which is of the AC source or the device. which is producing the AC voltage. Now we are going to look at a half-wave rectifier. We are going to look at a full-wave rectifier. We've already looked at a half-wave rectifier. A full-wave rectifier, meaning this one, the complete waveform will be seen at the output, meaning we will not only see half of the AC source, but we'll see most of it. But remembering that now the AC voltage is unidirectional. You do not forget that. Now it's in one direction. The negative part now becomes positive, such that we convert AC to DC. That's the goal of a rectifier, to convert AC to DC. We are going to look at two types of full wave rectifiers. We are going to start with the center tapped full wave rectifier. This stands for full wave rectifier. I was lazy to write everything in full, but you must understand. We are going to start with the center tapped full wave rectifier. We are going to start with rectifier. So let's look at a schematic diagram, or the circuit diagram of a general center tapped full wave rectifier. There we go. As you can see, there's our center tapped full wave rectifier. Okay, let me zoom in a bit. Yeah, I think it's fine now. Yeah, here's our full wave rectifier. So yeah, I guess you know what a transformer is. This is a transformer, and we have two diodes. Look at the difference between a full wave rectifier and a half wave rectifier. In a full wave rectifier, we have two diodes instead of one, and now the diode is isolated from the power source, from the AC source, using a transformer. As you can see, the transformer, usually we want to step down or step up the AC voltage. So with rectifiers, usually we want to step down the AC source, the AC voltage. So that's why we need a transformer, so that we reduce the amount of voltage to allowable levels or to non-dangerous levels, because voltages can be lethal. Voltages in our outlets are lethal, so that's why we need to step them down. So that's why we have a transformer there. The transformer there is there to step down the AC voltage. So here's our AC source. The AC source will produce an alternating voltage. Here's our alternating voltage. Here's the alternating voltage. This is the input voltage. This input voltage is now stepped down in this transformer part to safer levels. So the shape is still the same. The only difference is the strength or the magnitude of the voltage. The frequency is still the same. So Vin is still our Vin into these diodes. So let's look at how this AC voltage is converted into this pulsating voltage. Now, during the positive of the AC voltage, what happens? This is what we have. During the positive half cycle of the AC voltage, we have this. we have these polarities across the secondary terminal, the secondary windings, or the secondary part of the transformer. As you can see, one of the diode is forward biased, this one specifically. This one is forward biased, whereas this one is reversed biased, just because of the way the polarities are. So this will conduct, so this will allow the positive part of the cycle to come through and pass through, while this one is off. So the conduction path is this one all the way to the resistor, and this is what I have. This is the output voltage, and in the negative of the AC voltage, the opposite happens, meaning this one is now comes forward on this diode, and this will now allow the negative part of the cycle to pass through. Now look at the difference between a half wave rectifier and a full wave rectifier. In a full wave rectifier, we are rectifying both the positive half cycle and the negative half cycle. Both the negative half cycle and the positive half cycle are converted into DC voltage, whereas in a half wave rectifier we saw that we were only able to convert the positive half cycle of the AC source into a DC, but in this case we are able to do both in the full wave rectifier. So if we were to put a probe here and take a look at the output during the negative half cycle, we will see something like this appearing. Yeah, there we go. This one is due to the positive half cycle. And this one is due to the negative. This is the negative half cycle being converted into a DC voltage. Negative half cycle. There we go. Moving on. Analysis of a center tapped full wave rectifier. Just because we have a transformer, we will need to know the peak secondary voltage. The peak secondary voltage is given by this. The total peak secondary voltage is given by the turns ratio N multiplied by the peak primary voltage. The peak primary voltage which is from the AC source, where N is the turns ratio. It depends on you how you want to define the turns ratio, but I would say you should define it as the ratio of the number of turns in the secondary to the number of turns in the primary. Yeah, and this is the peak secondary voltage for each center tap is equals to the total peak secondary voltage divided by 2, and the peak output voltage is equals to the peak secondary tapped voltage minus 0.7 volt, which is the diode drop across one diode, because in each rectification cycle only one diode is on. You will see that when it comes to a bridge rectifier, 2 diodes are on, so you will need to separate 2 times the diode drop. Here's an example. Consider the following center tapped rectifier circuit. Here we have, here's our AC source with a 120 volt mean square voltage. This is not the peak voltage but the root mean square voltage. And here's our transformer, which is, as you can see, the turns ratio is 2:1, meaning the number of turns in the primary are 2 times the number of turns in the secondary. Do not mind the drawing. Drawing, it does not physically represent the number of turns. No, do not mind it. Just know that the numbers in the primary are 2 times the number of turns in the secondary. And here's our transformer. The voltage is stepped down. The AC voltage is stepped down to an AC voltage which is much lower and much safer. And after that rectification, the diodes do the rectification, converting the AC voltage into a DC voltage. Okay. So I'll give you some. You can pause the video and go ahead and try. Oh, you have not yet seen the questions first. Yeah, but you can pause the video, try the example and then see if you have answered correctly. That's
input voltage, the peak, because I've given you the root mean voltage. Calculate the total peak input secondary voltage each center tap. Calculate the peak output